Good afternoon. I'm Commander Anna Kahn. It's a pleasure to have you here with us today. I'm in the Division of Environmental Health Science and Practice at the National Center for Environmental Health at the Centers for Disease Control and Prevention. I'd like to welcome you to our third annual Epidemiology and Environmental Health workshop. Today's session will feature a presentation followed by a Q&A session with our panelists. Please note that all participants are in listen-only mode and closed captions are available for this webinar. Today's Nexus webinar will be available to view on demand in a few days after it's been recorded and we've reviewed over it. You can find today's webinar on CDC's Nexus website, cdc.gov/NCEH/EHSP/EHNexus, or you can scan the QR code. You may submit questions at any time during today's presentation. To ask a question using Zoom, click the Q&A button on your screen and then type in your question in the Q&A box. Please keep in mind that sometimes we get more questions than we're able to answer during a live session. Please note that the findings and conclusions of this presentation and this workshop are those of the authors and do not necessarily represent the official position of CDC. And now it's my honor to introduce Dr. Eric Svensson. Dr. Svensson serves as the Director of the Division of Environmental Health Science and Practice at the National Center for Environmental Health here at CDC. Dr. Svensson, the floor is yours.
All right. Welcome, everybody. Good morning. Good morning to you all online. And thanks to many of you who traveled here in person. This is the first time we've been in person for one of these workshops. This is our third workshop. This is the first one in a hybrid mode. So thank you for suffering through the security and getting here safely. So quick interactive activity here. So how many of you traveled more than 500 miles to get here? Okay, well, a couple of our speakers, and we have one in the audience. Where'd you travel from? Seattle. Wow. Anyone beat Seattle here in the audience? So you've got the biggest traveler award here in the audience. And online, I'm sure we have people in very awkward time zones listening in with us. So if you can put in the chat, can we do this in the chat? You know, the farthest away, folks that are 4, 5, 6, 7, whatever time zones away. We want to be thankful and sensitive to all the wonderful people who are logging in online. So is anyone watching that for me? So any word yet? Sweden. Thank you for joining us from Sweden. That's what, 6 hours, I believe, and 7. Long time. And others?
Alaska,
Argentina, Alaska, London. Wow. Indonesia. Well, right now I'm going to declare Indonesia the unofficial winner. And thank you for joining us from across the globe here today. We're thankful that you've been able to join us today. We're excited about the topics and what we're going to be able to bring to you today. So as you heard, I'm the Director of the Division of Environmental Health Science and Practice. And within the CDC, we are the Centers for Disease Control and Prevention. So we are in the National Center for Environmental Health. And our division is the division that is focused on building the best science to drive public health practice in the trenches and move it forward to advance public health and protect more people and save more lives. So oftentimes we have gaps in the applied epidemiology training that we get in graduate school, where we're trained up and how to be able to help folks regulate a chemical, because we can look at a single chemical and see what it does to the human body and everything like that. But it doesn't connect with the reality of the toxic soup that we breathe every day and the world around us that is much more complex than just that univariate type of artificial association. So we're excited to be able to bring to you some ideas of how we can look at that complex framework that public health is really in, to be able to move us forward and use some of those to help move public health. So again, this is our third year that we've been doing this. In 2022, we kicked this off, focusing on a lot of spatial methods in looking at cancer cluster investigations and different types of correlation studies and things like that. And then we last year worked on looking at causal inference and looking at models within epidemiology and difference in different studies, regression, discontinuity, and a bunch of other fun things. And if you don't think this is fun, then you're in the wrong room. But stick with us; you'll realize that this stuff is really a lot of fun. So, and then I already mentioned what we're talking about this year. So we have an amazing panel of speakers who you'll hear about here in a minute. But we're very thankful that we have our friend and colleague, Dana, who's been, Dr. Flanders has been leading us through these discussions for the last few years. And so thank you, Dana, for helping to coordinate all this and to pull this together in a meaningful dialogue. And we're excited to have this interaction today. So my main job is done. Just wanted to get you feeling comfortable. Welcome. Is someone going to give logistics announcements here too? So we'll do that so you know where to go for various things. You already found the water and food. Sorry, we can't get that to Indonesia, but at least you're here with us this morning. So with that, I'll pass it back over to you.
So speaking of logistics, so a couple of things. So there's a couple of options available. There's restaurants across from CDC, which I'll look for the names of those so I can provide those to you that are in person. And then also there's a cafeteria here as well. And we're going to find out what's on their menu as well. But with that being said, we want to make sure that we give you that additional time needed to make sure that you're able to get lunch and be able to enjoy it as well. So without further ado, I want to go ahead and welcome Dr. Dana Flanders, a professor and in the Department of Epidemiology here at Emory. So, sir, the floor is yours. Thank you, Dana, so much.
Well, thank you. Thank you for the intro, and welcome to all of you here and also to those of you online for this workshop on environmental mixtures and epidemiology. I must say that putting it together has been a group effort, and so I really deserve only a very small amount of the credit. But anyway, we're excited. We have a great panel today. Dr. Kioumourtzoglou, Associate Professor at Columbia, Dr. Chris Jennings, Director of Biostat in the Department of Environmental Medicine at Mount Sinai, Dr. Vishal Midja, biostatistician and environmental epidemiologist at Mount Sinai, and Dr. Jennifer Baum, Associate Biostat Investigator at Kaiser Permanente in Washington. A really excellent panel to talk about environmental mixtures in epi. So that we don't get behind to start with, let me introduce Dr. Kioumourtzoglou. So, as I said, she is a environmental engineer and epidemiologist. with a Master of Science in Public Health from Environmental Sciences at UNC, and a Doctor of Science in Environmental Health from Harvard School of Public Health. She is currently an associate professor at the Department of Environmental Health at Columbia's Mailman School of Public Health. And her research is focused on implied environmental epi, including quantifying and correcting for exposure, prediction, uncertainty, propagation, and assessment of high dimensional and complex exposures. Her studies have mainly, but not exclusively, focused on air pollution and other climate change related exposures, and additionally on identifying vulnerable subpopulations and characterizing how risk may vary across neighborhood level and other urban characteristics. So Dr. Kioumourtzoglou, could turn it over to you.
Thank you. Good morning, everyone. And by the end of the day, you will all be able to say my last name. Otherwise, no one's allowed to read their. I'm joking. No one has to say my last name. I was tasked to provide an overview of how to start thinking about mixtures issue. I'm the only non-biostatistician in this panel, so I guess I'm also the translator between, the statistics world and things our minds can understand, or my mind. I was very excited. I'm very excited to be here. Thank you for the invitation. It's my first time at CDC, and because I was so excited. This is a very long presentation, which means I tend to talk when I have long presentation rather fast. I'll try to monitor that, but if you think that it's going offline, like too fast, please, make a signal, tell me to slow down, and I'm happy to do that. And I can also stop at any point if we're running out of time. And with that, are we ready? And shared? Oh, not yet. Perfect. Thank you. Excellent. So this is just a brief, and if online you cannot hear me well, please make a note on the chat. Good morning, everyone. So this is just a brief outline of what we'll talk to today. We'll start with an introduction. Traditionally, most epidemiologic work has focused at one pollutant at a time, and that has worked very well. That has led to, regulations that protect us. However, it's very well recognized that we need to assess our exposures as a mixture because we are not exposed at a single thing at a time. So the million-dollar question is, how can we represent the complexity of reality in a single statistical model? In this presentation, I will mostly discuss methods to assess exposure to mixtures for epidemiologic studies. And if you want, during the discussion session or the Q&A with everybody, with my fellow presenters, we can discuss potentially different considerations for talks and risk assessment studies as well. But first of all, what is a mixture? And actually, there's no strict definition. When NIHS had the request for applications to develop methods for mixtures, they defined the mixtures in that specific context as that must have at least 3 independent chemicals or chemical groups. But in general, a mixture indicates exposure to multiple stressors at the same time. And we tend to think mixtures as chemical stressors, and I may say chemical exposures, chemical mixtures during the presentation, but it's important to know that these mixtures are not only chemical exposures, right? We are exposed to non-chemical things as well, including socioeconomic factors, built environment, diet, etc. The most important thing when it comes to mixtures analysis is what do we want to know? What do we want to learn from this mixture? Depending on our research question, we will identify different methods that may be more or less appropriate for our research question. Because, when you have 10, 15, 100, a few thousand exposures to work with, you can ask many different questions. And my colleagues, collaborators, and I have been thinking of what these potential questions might be. And we've come up with these 6 now questions, but there might be others. And again, we're happy to discuss if people here have other ideas. And these are can I? No, maybe not. I can use this, I guess, so that people online can also see what I'm pointing at. And so we can have toxic agent identification, overall effect estimation, exposure pattern recognition, mediation, interactions, and a priori defined groups. And during the next 40 minutes now, I will go into a little bit more detail in every one of these. Wrong way. There we go. So this is now an old graphic. And if you notice, it doesn't even have mediation in it. We put this together when we started thinking about potential. This is not an exclusive list of methods, but when we started thinking about which methods can help us answer which research questions. And these are the new methods that were developed under NIHS Prime. And these are not only the newly developed methods. So this is a very, very active field. There is a new method coming out pretty much every month. So this is exploding. So this only emphasizes the need to have a very well-defined research question, because otherwise we can get lost in all the methods that we can use. And today, I will not be presenting any details on any specific methods. I'll bring some examples, of course, but in one day, it's impossible to cover all of this. So my colleagues will be presenting examples of methods that they have developed, but it's not really easy to cover all of these. So when we start a mixtures analysis, there are a few things that we need to consider. First of all, based on our primary research question, different methods are appropriate. There's no single method, one, that can answer all relevant research questions at once, and two, that it would outperform all other methods for all potential research questions. So that's extremely important. Other considerations to keep in mind is that we want interpretable and robust results coming out. In environmental health, our priority, not exclusively, but our priority is to understand links between exposures and health. There's some prediction involved. We're not talking about that here. So if we use black box methods, then these do not help us understand links between exposures and pathogenesis. Also, robustness. Many methods are not necessarily robust, means you change something a little bit and then you get a completely different answer. And maybe that answer looks very interpretable, but if it changes every time, then is it really interpretable? And it's definitely not robust. So when choosing methods, we need to keep this in mind. Computational scalability becomes increasingly important. Not only in the exposure matrix, are exposures becoming, especially now with omics, several thousands of features, right? But also in the number of units, whether there's a people, counties, cities, whatever that we have. There are studies now with millions of people, entire Medicaid, nationwide Medicare, et cetera. So if that's the world, the realm of analysis we're in, we need to identify those methods that can, not break our computers. Exploration versus hypothesis testing. This, thankfully, is increasingly not so much of an issue, but when these mixtures methods first started exploding, there were many papers that came out that the results didn't really make much sense, but the bottom line was but this was an exploration. This was not hypothesis testing. We were just wanting to see what happens. And that's great. We do need exploration. That's what moves, the science needle forward. But if those results are useless, then we're just going down a rabbit hole, right? So even if we are in the exploration space and not very well-defined hypothesis testing space, we still need robust and interpretable results. And finally, there are so many other fields that are way ahead of us in this. There's machine learning, and there's, other biostatistics, non-environmental statistics, but other parts of biostatistics that they have been developing methods that are extremely useful, but they were not developed for our needs. So if we just blindly take a method and run, then, we don't know what the answer is. It was not developed to answer our questions. So we may need to, one, understand what that method does, use it, definitely use it. That's how, again, interdisciplinary work, that's how we move forward. But understand what it does, and we may need to adapt those methods for our specific needs. So I'll start going over those big bubbles of research questions, and I'll give what they mean and an example of each. So first of all, exposure pattern recognition. This is something that I personally work a lot with. And why should we care about identifying exposure patterns to chemicals in a population? Or as I said, even though I may be using chemicals, I mean in general stressors. It might be other non-chemical stressors. First of all, this can be specific sources or behaviors in the population that give rise to the mixture that we see. So then if we link those patterns that we hopefully can interpret as our specific sources, or behaviors, then that can result in much more efficient regulations and targeted interventions. It's much easier to regulate traffic versus regulate, only one PAH that comes out of a tailpipe, right? Polycyclic aromatic hydrocarbon. This is predominantly a class of unsupervised methods. Unsupervised here means that we identify the patterns independently of the health outcome. The health outcome does not inform the solution. But for most of these methods, supervised extensions exist. And supervised here means that we identify those patterns that are relevant for one outcome specifically. Which version we want to use really depends, again, this will be a recurrent theme on the research question. If we want to inform regulatory action or interventions, then maybe we do want the unsupervised version. If we want to better understand specific biological pathways for a specific outcome or disease, then maybe the supervised version is more relevant. So I'm going to give you one example. This is principal component pursuit coupled with non-negative matrix factorization. PCP is a much better version of PCA, basically, and it's a method that was originally developed for video surveillance that I've worked with a lot with computer science. It's a whole different language. That was fun, but to apply for environmental health analysis. So PCP decomposes the exposure matrix to a low-rank matrix that includes all the information about the specific patterns, and a sparse matrix that includes information about our mixture that cannot be explained by the patterns. And then NMF, non-negative matrix factorization, assumes that the measurements in the low-rank matrix, in this case, arise from F underlying sources. Common application, you may have heard, is air pollution or particle source apportionment. Non-negative matrix factorization. Thank you. And yes, please feel free to stop me, ask questions. I prefer a more interactive, yes. But I cannot monitor the chat. So if we have chat questions that need to be answered right away, thank you. So a student of mine, Rachel Tao, phenomenal student, used data from New York City from 2007 to 2015. The outcome was myocardial infarction. And we used information from daily PM2.5, total concentrations, total mass, and 26 of its components. And we used first PCP and NMF to identify different sources of air pollution in the city over this time period. And these are the sources that we identified. So we identified crustal dust, salt, traffic, regional or secondary air pollution. And these three single element sources that didn't fit in one of the more broad sources that we identified. And then in a second stage, she ran a case crossover study design. And she identified that total PM, that was not surprising, of course, was associated with elevated risk for MI, and so was regional. Traffic had a few outliers. This is including the outliers. Once we excluded those from analysis, it also was pretty risky for MI as expected. So, this is one example where now we can regulate traffic specifically, which might be more effective than general PM2.5. That's an indicator of the overall mixture. issues or considerations when we're thinking about exposure pattern recognition. First, there's no gold standard to pick the number of factors or clusters if we were doing clustering. More recently developed methods like PCP try to address that. So one of the outputs of PCP is the optimal number of sources or factors or patterns. Usually that is, the user has to pick a solution, which can have implicit assumptions there. Results are not easily interpretable, especially for biomarkers, for example. It's easier if we're looking at correlations at things in the ambient air or in, our sociodemographic or built environment. But when we're looking at biomarkers, metabolism also influences these correlations across chemicals. So then that's maybe a bit harder to map back to a specific source or behavior. Factor clusters are assumed as truth in the health models. Even the example I just showed you before, right? We got the signal for traffic and we just plugged this into our health model. However, there is some uncertainty in us calling that, factor traffic. And if we don't account that into our health models, then we've shown that there might be some bias, and definitely the inferences are a little bit off. And again, most methods require implicit assumptions for solution selection. Moving on, identification of toxic agents is our second big bubble, which asks the question, which chemical or chemicals, stressor or stressors, in my mixture are related to an outcome, inherently supervised by definition. And this group of methods help us estimate chemical-specific independent associations while accommodating for the potentially very high correlations among mixtures members. The example I'm going to give is elastic net. This is a binarialized variable selection method that combines the L1 and L2 penalties of lasso and ridge. I won't get into details now. What this means, if you have questions, let me know. But what it means is it shrinks weak coefficients, small coefficients, down to 0, and coefficients of correlated variables to each other, so they are more similar. This is an example, Ladner et al. A few years back. They wanted to look at environmental contaminants and birth weight. They used data from more than 1,200 term single infants from Greenland, Poland, and the Ukraine. And they looked at phthalates, PFAS, and 2 organochlorines. And they used elastic net. So this top table here shows the coefficients. And you see all the zeros. This is when elastic net shrinks coefficients to 0 because they were small. So, and this is the further adjusted. They also included a few more covariants in the second model. So what these authors did is this now, using this, we can identify which of all these chemicals are, more relevant for this outcome. And what they did then is they used these adjusted ones in a second stage linear regression, adjusted for other things to get their final effect estimates. Now, I've seen this happen a few times. This is not great because it ignores, again, as we were saying in the previous example on pattern identification, it ignores that we ran this entire model before, right? And assumes that we knew a priori that these are the important ones. So that's not great, but this first stage is exactly picking up those chemicals that are most predictive of the outcome, of this specific outcome in this specific mixture, in this population. Most methods, when we're thinking about bad actors, I wouldn't say now most, because this has been getting better, but many methods do not estimate parameter variances, elastic net being one, lasso, group lasso, etc. So we don't get standard errors. And standard errors are important for us to understand, how confident we are in those results. The critical window of exposure and chemical half-life is a potential issue if measured in biosamples, right? Is different chemicals have different half-lives. If I throw in my mixture something that's, has a 3-day half-life versus something that's a year half-life, then, maybe the one with a 3 doesn't show up in my analysis. That does not mean that it's not important, right? And the toxic agent might not be even included in my mixture because I don't know how to measure it. I don't even know that it exists, but it might be correlated with some of the mixture members. So it's possible that I pick something as, this is my toxic agent here. And in fact, it might not be that. That might be, correlated with something else that I did not include in my analysis, or that was measured with so much measurement error that it was just not picked up. Moving on, interaction among mixtures members is another, of the bubbles. These are actually two different classifications, interactions and nonlinear exposure response curves. These methods tend to do both, most of these methods. However, nonlinear relationships is not a research question. That's an assumption that most models make. And as an assumption, we need to test it, but it's not a research question. The question is A associated with B? It's not like, is it linear? Well, I guess unless it's very specifically defined as, is this association linear? But that should then be the research question. And even in that case, nonlinearity should be explored. Rant aside, let's move on to interactions. If there's reason to believe that the combined health effects of a few stressors is greater or less than the sum of the independent effect, that can, hint to potential synergism or antagonism. Most methods, almost all methods, can accommodate a priori defined interactions, right? I can estimate the product between two variables and put that in as a new variable in my mixture. However, one, we need to hard code this. Two, we need to have some a priori idea of which interactions specifically we want to test. And three, if it's more than one or two, then we're running in dimensionality issues, because then you imagine all 2, 3-way n-way interactions can blow up our models. So if we don't really know which specific interactions we want to look at, semi and non-parametric methods are preferred because they're more flexible. Example here, Bayesian kernel machine regression, and I think Jen will be talking much more about this. This is a model that very flexibly models the full multidimensional exposure response surface, including higher order interactions. So this example here was looking at insecticide exposure and girls' body weight using data from a prospective South Africa birth cohorts. And we're looking at peri-delivery maternal pyrethroid metabolites and organochlorine pesticide concentrations. And the outcome was the weight of age at 1 to 2 years old girls. The results for girls specifically are shown here. On this side, on the left side, these are the exposure response function for each of the 6 chemicals examined. So this BKMR also can help us look at, identifying individual levels. So that goes back to the beta actors that we're talking earlier. But the reason why I'm presenting it here is for the interaction. So this plot here shows for each of these chemicals, what is the effect from moving from the 25th to the 75th percentile of that chemical when all the other chemicals in the mixture are at the 0.05 percentile in red up to the 0.95th percentile of their distribution. So if there's no change, like this is DBCA, then this chemical here doesn't really interact much. It doesn't matter what level all the other chemicals are, the effect size doesn't change. However, for something like PPDDE or 3-BPA, we see that this actually changes. The effect of this chemical changes depending on how high or low the concentrations of the rest of the chemicals in the mixtures are. So we can look at these interactions this way. And I make a note here, I said that BKMR here also helps us identify independent chemical-specific dose response curves or exposure response curves. Many methods can help us answer more than one question. Not all questions, research questions, but more than one. So here I'm giving examples of what each method does, in my opinion, so disclaimer here, best. My collaborators may disagree with this statement. Yes.
On the left-hand panel,
This one.
including that increased weight is good for girls in the study. Comment, that show increased weight, increased exposure to BCCA, because I've seen this in other data model papers also where there are awkward releases. I mean, I think it's real. It should be like practical discussion. But do you have any comments on observations like that?
So I cannot talk about this specific example because this is really, I've never worked with these insecticides. I don't know even what they stand for. So I don't have any a priori hypothesis. Also, I don't know if weight, I'm guessing weight in South Africa, higher weight is better versus I guess in the different countries that higher weight might be, right? But this is an area that I really know nothing about. So I cannot comment on that, I'm sorry. But I thought this was a very nice example of BKMR. Now, the question though on this is whether this is a BKMR specific, I don't know, issue. Jen might be able to answer when she presents later more, and we can talk more about in the Q&A. But we're still dealing with very high dimensional exposures. This is a relatively small sample size. I don't know the correlations between these things. So it's very different if you're dealing with a mixture that has correlations up to 0.6, 0.7 versus a mixture that has correlations up, 0.99. And if you only have 700 people, I don't know how much that comes into play in the solution. And that's not a BKMR specific concern. That would be an issue with any method, right? The sample size and the correlations you're dealing with will be an issue regardless of method. But I don't know if that answers the question. So Jen, you have homework for later. Sorry. Now, considerations for assessing interactions. These semi and non-parametric methods, this may answer part of your questions, can be very, very, very flexible. Assume, I've seen Brent Kuhl present on this many times, and the way he presents it is, if you're familiar with generalized additive models and penalized splines that are for one chemical only, and you have one high influential outlier, that can throw off the entire, exposure response curve for one chemical. Now imagine that in this case, a 10D space, right? So outliers become way, way more important here, and they can influence the entire solution. So sensitivity analysis, removing potential outliers are important. Some methods can be very unstable, such as regression trees, if not in a random forest company. There are more robust alternatives, for example, random forest or samples of trees and/or BART. We may lose some interpretability if we just use a random forest, because now that's a black box. We cannot extract interpretable. We can couple those with G-estimation, and that will give us a nice exposure response curve. So there are solutions. So this is a promising area for sure. Still being developed. So a priori group effects. Let's say that we have some prior knowledge or hypothesis on how chemicals may naturally group in the environment or may share a pathway to toxicity. Now, remember, the first one we wanted to identify patterns. We didn't know what the patterns are. This is, what if we know the patterns and we want to identify to characterize the effect of a pattern, right? So methods exist to allow estimation both of group and within group effects. And the example I will give here is structural equation modeling. This is by no means a new method, definitely not developed for mixtures analysis, but can be very helpful for sure. Researcher-defined groups are represented as latent variables. Latent variables represent what is common among group members. So the latent variable only represents the shared variability across the members in the group. And SCMs have two components, the measurement model, which links the chemicals to the latent variable, and the structural model, which links the latent variables to the outcome. all in one analysis. So this example is on traffic pollution inflammation. You may notice that there are many air pollution examples here. That's my area, as Dr. Flanders said, of expertise. So that's what. So if you have any questions about this analysis, let me know, and those I can answer. So this is an NIS analysis. This is a cohort of veterans who reside in the greater Boston area. The outcome here was inflammation. Traffic was the specific exposure of interest. And the authors used these three gases in black carbon, that's particle phase, to represent traffic. And they ran a Bayesian SEM. And the group here was specific air pollution source, i.e. traffic. So this is a latent variable traffic that gives rise to these traffic-related gases in black carbon. So they use 7-day traffic exposure as an average. And the result here was that they found that increases in traffic resulted in, I think an IQR, so I didn't include this here, resulted in 11.1% increase in risk for inflammation in the IS. So consideration where estimating group effects is not as developed as other mixtures categories. The definition of the groups results requires a lot of expert knowledge coming into this. And ideally, we want to combine it with pattern recognition instead of a priori defining groups. But it'd be nice to have everything in one analysis. All right, mediation. Caveats. I do not understand mediation, so I'll do my best to describe this. But mediation is not a very well developed in a mixtures context, but it helps us understand pathways and estimate natural, direct, indirect, and controlled direct effects of a complex mixture exposure on an outcome through a mediator. Now, this one method that has been specifically developed to look at mediation in a mixture setting looks at the exposure is a mixture, but the mediator is one dimension, is one mediator. This is called BKMR, causal mediation analysis, the method CMA. It assumes for now, I know the authors are developing extensions, but for now it assumes a continuous outcome, one mediator, and the mixture is the exposure. It allows for effect modification, so both in exposure and outcome models, which is important when we're thinking about mediation and in presence of modifiers. It assumes no exposure mediator, and outcome, and exposure outcome, residual or unmeasured confounding. That's a general mediation assumption and general epi assumption, really. And it allows for variable selection in the mixture because inherently it's BKMR. So the example I'm going to give is the investigators look at metal exposures in utero, mediated potentially through birth length, that was the question, and neurodevelopment was the outcome. So that's a prospective birth cohort in rural Bangladesh, in utero exposure to these metals. They used daily scales for neurodevelopment. Modifier was age and test. So the results that I'm showing down here are the results only for the younger age, so the 10th percentile of age. I don't remember up to what ages they looked at. These are young children in any case. This is the overall effect, metals to neurodevelopment, higher metal concentrations, worse neurodevelopmental outcomes. We've discussed this. This is for the main effect, like the total effect, sorry. So they did not see interactions between the metals. And this is the new output. So these are total natural direct, natural indirect, control direct effect at the 10th percentile and the 50th percentile and the 75th percentile of the mediator. And in these two first lines are the BKMR results. With and without variable selection, these are very similar. The variable selection, once included, just helps with efficiency and precision a little bit. And the other lighter colored ones are more traditional mediation analysis. And basically we can see, and they also showed with simulations, that we can identify better the total direct and, well, direct in this case was null, but natural indirect effects and control direct effects with this method when we have a mixture versus otherwise. So considerations is though that oftentimes we have very high dimensional mediator. For example, we have one or many exposures. We want to see, are they associated to my outcome through the metabolome, transcriptome, etc. No method yet exists for high dimensional exposures and mediators. Current studies have used dimensionality reduction methods to reduce the dimensionality of high dimensional mediators. But, interpretability, we've talked about these issues before. This method has only been evaluated for up to 10 mixture members. So that potentially doesn't mean it doesn't work for larger mixtures. We don't know that yet. And it's very slow. So I think this analysis, 700 people, took 5 hours or something, they say in their paper. So that's a limitation. Finally, overall mixture effect, and I need to speed up. We may want to estimate the overall mixture effect of a mixture. That is, as chemical concentrations in my mixture increase, do we observe corresponding changes in the outcome? If everything goes up, yes. So I'm going to give 2 examples for this, one unsupervised and one supervised. The unsupervised one is we can create an overall mixture index independently of the outcome. So I've seen in several papers that people, for example, sum the standardized concentration of the mixture members. If you have, for example, a mixture of 15 PAHs, you standardize them so they're all on the same scale, sum them up, and that represents your mixture exposure. Another way, and that doesn't work with all mixtures, this is very specific to dioxins, but it's nice. We can sum weighted concentrations based on some prior overall toxicity knowledge, like toxic equivalency factors, for example. And then I'll also talk about weighted quantile sum regression as a second example that creates empirically weighted index of chemicals based on chemicals quantiles for the specific outcome of interest. This is a weighted index that represents, the weighted index represents the overall mixture, and the weights then can also help us get the relative variable importance, so we can get an idea of toxic agents as well. So the first one is on persistent organic pollutants and leukocyte telomere length, and in his study, this was the mixture. They used the TQ index for those chemicals that had toxic equivalency factors. So that's not everything. And this is the last column here. And they found that each doubling of the TQ resulted in a 5% increase in leukocyte telomere length. And these are effect modifications by these factors that the investigators wanted to examine. Moving on to WQS. This is a study looking at phthalates and thyroid hormones in the home study. This is a birth cohort. The question was, is there an association between maternal exposure to a phthalate mixture during pregnancy and newborn thyroid hormones? So they use quartiles of phthalates. WQS, Chris will talk a lot more about this later, breaks down training and testing, or you estimate the weights in one stage in some percentage of the data, and then the index effect. In the rest, they don't say the split here. It's usually 60 to 40 or 80 to 20%. These are the overall effects. They looked at 2 thyroid hormones, the log of TSH and TT4, and they found that this mixture resulted in decreases in both of these. That's the overall effect. These are not histograms, actually. These are the weights representing each of these chemicals by color. So the most important one for TSH was this green one that's, I'm sorry, I don't know my phthalates, MBZP was the most important one for this association, whereas for TT4, the blue and the black one seem to be the more important ones. MEP and MIBP. But you can see how we now can estimate overall effects with WQS. So consideration, supervised versus unsupervised. The supervised gives us a combination of exposures relevant for one outcome, the outcome of interest. The unsupervised, this is very similar to what we talked 20 minutes ago now. The unsupervised gives a combination of exposures independent of any outcome. Toxic equivalent factors, unfortunately, are only available for dioxin-like compounds. Most studies just some concentration, maybe after hopefully after standardizing, but that assumes equitoxicity, which is, kind of breaks the point here. New methods are being developed to create an index of overall burden. For example, Shelley Lewis developing the PFAS burden score based on item response theory. Glenn McGee's developing a BMIM. I never remember what that stands for, but there's a lot of development in this area as well. And again, choices always depend on the research question, so we always have to come back to that. So in the last 5 minutes, very briefly, I'll talk about some overall considerations. I'll keep saying it's very important to have a well-defined question throughout the analysis. Sometimes we deal with very, very high correlations. If we don't have the sample size to be able to absorb those, no method will perform excellently in those cases. Expert knowledge is always helpful for the outcome, for my mixture. They can help us understand what's going on more than if, we just run the analysis. Also, I said that as from the analyst perspective, also from the exposure perspective or the health outcome, the epidemiologist perspective, it's very important to have expert knowledge on the biostat side to help us with the methods, to apply the methods. If something doesn't work, I may need to know why it doesn't work and how can I fix that. Prior knowledge and toxicological or biological input, if I can incorporate that, or if I can make explicit my assumptions that drive my choices, that's very important. We talked about interpretability of solution and robustness. Many methods currently used in other fields such as machine learning are extremely promising. They were developed to deal with high dimensional, high correlation data, but they were developed for prediction. So just taking them off the shelf and using them might not be great. So we may need to adjust. That's why biostatisticians are our best friends. They can help us with that. We talked about two-stage models in a couple of examples that leads to invalid inferences, which are also very important for public health. So it's important to be able to at least have an understanding of how off we are. Exposure measurement error, true in any environmental epidemiological study, really, depending on the error. If some of my mixture members are measured with more error than others, then can throw off my entire solution. So I need to have some understanding about how much error is in it for each chemical, with how much error each chemical is measured. Generally, a good practice to compare results from different methods that complementary, that help answer the same research question, right? I cannot compare a PCA solution to BKMR solution and expect that the results will be the same. They answer very different questions. But within research question, there are multiple methods that can help us. So we need the sensitivity analysis to assess robustness of our results to the choice of method. Consistency is more likely across research questions if the associations are linear and no interactions are present, but by no means it's guaranteed. And we need to keep in mind that when we detect differences across methods, that could be because they are developed for different research questions. And trying different methods and choosing the answer we like the best and only publishing on that should always, 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 always be avoided. One more other important consideration in exactly 3 minutes. So we'll see if we have time. So many of these methods have some randomness in them. SL here stands for statistical learning, either to randomly split data or to start from random starting points to begin sampling in Bayesian analysis. So that's where seeds are important. And most of us have heard in our classes that we have to set the seed, because if we don't, we'll get different answers. So we all set the seeds, which brings the questions, but how different are the answers and how important is this for the results that I present? So we went on an exploration to see how different the answers are. This is the data set. I showed this for the TQ example in overall effects, the same data set. And we used three different methods here, lasso, WQS, and BKMR, and varied the seeds to see how much the results will change. 100 seeds for each analysis. So these are the results over the lasso. The lasso has this penalization lambda parameter that has to be estimated, usually with cross-validation. If lambda is 0, we talked about elastic net. If you're not familiar with lasso, for now, think that it's similar to elastic net. It's not exactly, but it's in that area. So if lambda is 0, all exposures are included in the model. As lambda goes to infinity, all exposures are pushed to 0. So none of them is important. So you can see here with red, each line here was one seed, a different seed, 100 seeds. The solid red line, that was the median lasso, the median lambda selected. These IQR lambdas are in the proximal dashed lines, and this was the maximal and minimal lambda value selected. So these are the results. These are on the x-axis are the 18 congeners that we looked at. On the left y-axis are the beta coefficients, their value, and on the right y-axis is the percent, the percent of the times out of the 100 seeds that the coefficient was non-zero, was not pushed to 0. So the columns are for the y-axis, and the points for the right y-axis, and the points are for the left y-axis. So here, this congener here, this is a furan, had higher coefficients, right? All the dots are high, relatively, precise. The variability wasn't large, and it was selected 100% of the times. So this one, these 4 ones were picked 100% of the times. But some of them, like this one, even though it was picked 100% of the times, the coefficient varied quite a bit. And there were others that were picked, 10% of the times or 50% of the times. That means that depending on the seed, I could have concluded that this is important or this is not important. These are the results for WQS. So we did this. This is very similar. Actually, WQS is the only method that now has an official version to incorporate this. That's the repeated holdout. And Chris will talk a lot more about it. But this is a similar plot, right? So this variable, this is the same furan, was picked almost 100% of the times with high weight. This is above the threshold that the weight was deemed important. Chris will talk about what that means because I'm running out of time. So I'm getting into her time, sorry. But you also see that there's some variability in how variable these coefficients, the estimated coefficients are. And these are the results for the overall effect. As you can see, in this case, except from 3 seeds, the overall effect estimate was always significant, but with great variability. The red one here is the pooled effect estimate. And finally, we also did it with BKMR. BKMR is a little bit different because it doesn't have splits, but still the change need to start from a certain point. We would expect that BKMR would not have this issue. Indeed, in 96 of the seeds, BKMR did not have an issue and the results were very consistent. In 4 of the seeds, BKMR, I'm going to dismiss this. Is that okay? Okay. I dismissed. Me neither. Hopefully we won't have to find out. So this is the furan that was very consistently picked with all methods, right? So 96% of the times, BKMR showed a very, very consistent association. For 4 of the times, BKMR flattened out. And we looked at those trace plots and it seemed to converge. Maybe it got stuck in a very weird, local place and it couldn't get out, escape from that. But if we had started from a seed, that could have resulted in a very, very flat line. So in conclusion, all methods we examined exhibited some seed-dependent variability in results. The degree of variability differed across methods and congeners, and might also lag with sample size. In this case, we had the same sample size throughout the analysis. So this is something we cannot really ignore. Results can vary. So in addition to sensitivity analysis using similar methods to answer the same research question, it's also important to run sensitivity analysis for the seeds we select and help evaluate their robustness and interpretability. And I don't mean we all have to run 100 seeds for every analysis. That will take forever. We'll never be able to publish anything, but at least try with a couple of seeds. If the results look similar enough, we're good, that's fine. But if the results vary a lot, then maybe we want to run several seeds and present those results, as those results are actually more honest to characterize the variability and the confidence we have in the associations we present. These are all the wonderful people that have helped me think through these, publish papers with these, develop methods, and it's an amazing team to work with. And with that, I'm only slightly over, miraculously. So this is my email if anyone has any questions at any point, but we also have a few minutes for Q&A here.
Yes, well, first join me in thanking Dr. Kioumourtzoglou.
Thank you. And you can really call me it's fine.
That was a very nice overview. Perfect, actually, I think covered a wide range of very relevant topics and gave us a good starting point for the more detailed talks on specific methods that are going to come. If you have questions in this room, please go to the microphone. We do have one from one of the listeners, but our online viewers. But while we asked for a little clarification, we haven't gotten back yet on that question. But in the meantime, let me ask you a general expansion. If you could expand a little bit on what you said about PCP, especially versus PCA.
Yes.
And just a little more insight about that if you could.
Absolutely. So and I wish I had the extra slides so you can see the photos. So what PCP does is it basically takes your full exposure matrix and it deconstructs it in that it reshuffles it. The developers of the method call it robust PCA, and it started as robust PCA. It was developed by computer scientists initially for video surveillance. And I was in a very random setting when I saw the presentation, and the way they showed it is they were showing video frames from a video. It was 3 columns, video frames. In the second column was what didn't change in the frame. So it was a mall. So it was all the same features in the mall, the buildings, the structure. And in the sparse, the third column was the sparse, where the people moving around. So those are the outliers. They are not part of, the patterns in the video. So I thankfully, one of the developers was at Columbia. So I emailed him and he was very nice to report back, because I was like, okay, this is what we need. It looks robust, it works. So what PCP does is PCA, it's very susceptible to outliers. PCA, factor analysis, and MF by itself, they are all susceptible to outliers. Because PCP breaks down and pulls the outlying values are not just high values, right? If a high value is consistent with a pattern, then it's part of the pattern. So users cannot do that before entering the data into PCA, because maybe they remove a value that's actually very important for the solution. The way PCP works, it does it, I don't really understand the math behind it, but it's all machine learning to me. But it does it in a consistent way, in that it keeps in the low rank matrix the structure of the data that represents the patterns that give rise to the values that we see, and everything that's an outliers that it's not explained by the patterns, that goes into the sparse matrix. So it might not only be the super high values, occasionally it's actually very low values, or mid of the thing values that cannot be explained by the patterns that are in the low rank matrix. We ran it when we were submitting the proposal. We had a grant to develop this. We ran it on an air pollution example. And if I don't know how much familiar you are with source apportionment air pollution, but most studies that do source apportionment remove days around 4th of July because of the fireworks, and then potassium is so high that it throws any solution off. So they just remove those days. PCP doesn't have to do it. It was so when my collaborator ran these as preliminary results and showed me the sparse matrix, with 2nd of 6th of July, potassium and blood camber popping up. And then we found nice sources, identifiable sources. I was like, I wish I had that as a PhD student when I was trying to do source apportionment. So it works very nicely. And we've now used it. We use it in source apportionment and air pollution. We've used it to create indices. We've used it in neurodevelopmental, looking at endocrine disrupting chemicals and behaviors, so we can detect behaviors in the population that give rise to endocrine disruptive. So it's been working very well, but I will say, and that I guess is a very learning experience, working with computer scientists was very, very interesting. I realize we have very little time. I'll pause here. We'll talk about this on a break, but that's it. Ask me about that experience.
That was gave some good insight. So thank you. Did you no?
We
Okay,
have 6 minutes yet to go.
we do have a couple of minutes.
We're not completely run out of time. I just wanted to make sure there's time for more questions.
Of your help with the computer, we keep getting these messages that pop up. If that can be.
I fixed that. I snoozed everything to a week from now.
Your presentation about seed sensitivity analysis was very interesting, and maybe I'm pushing the analogy a little too far, but it brought to mind my general concern when assessing mixtures, especially with things like phthalate. There are lots of congeners, the cursive dimensionality, and I'm just kind of curious for you in your work, where do you feel that you've encountered it and that has been problematic to have so many components to a mixture and then trying to assign, associations amongst all those different components?
So if I have, that's my personal, what I do. I don't know that everybody agrees with that. If I have very high dimensional exposures, that's more than 100, right? Then I try to screen them out, especially in omics analysis. I try to exclude features or chemicals that don't vary a lot in my population, because they may be very important in the mixture, but if they do not have variability, they're just dead weight. Understanding but they just take degrees of freedom without contributing much, right? So I try to screen and make that very explicit and include that. But that's an issue, right? And unfortunately, there's no way that we can guarantee, like, if everything were measured greatly and consistently, and if the distribution of modifiers across populations was exchangeable, there's so many things that come into play when we go from one chemical or two to 100. So I don't have a solution. I think running different methods, running different seeds, if there are consistent patterns, pun intended, if there are consistency in what we pick, I trust that mod. If the congener only comes up in one analysis and never again, it doesn't mean that it's not important, but that needs more investigation. That one furan that popped up in all analysis, all methods, all seeds, yes, that's clearly important. So that's how I proceed, and that's how also in papers interpret and then draw my conclusions. Yeah.
I think we should, can you save your questions for the roundtable this afternoon? We'll have additional time. I'd like to keep a little bit on track here. Well, thank you very much.
Thank
That
you.
was a great introduction. Tom.
I'm very sorry I talked too much and it wasn't enough
No,
time
it
for
was
questions.
great. It was great.